Thank you. So hi, my name is Jan. On the slides you might, or on the little cards here, you might see that this was supposed to be presented by Fatime. Unfortunately, she couldn't make it today, but I'm here to take her spot. I'm a blockchain researcher at Quantstamp. We're a Web3 security company, and we're going to talk to you about how to check for some errors in Halo2 here today. Also, if you have questions, feel free to ask me at the end or find me. But my colleague Mohsen is also here. He's sitting somewhere over there, and if you find him, he can also answer some questions about this. So let's get started. If this works. OK, too far. OK, so I won't introduce entirely what Halo2 is, because I think a lot of people here are familiar, but I will give a very high-level overview in case you aren't familiar with this proving system. So Halo2 is essentially a zero-knowledge proof library that's written in Rust. It uses Plonkish arithmetization, so it's based on the Plonk proof system and some modifications to it. And essentially, circuits are tables, and then we add some polynomial constraints over those tables. So here we can see an example of a table that would represent some sort of a circuit. You know, it's got some values in it. I don't know if this is a real circuit. It almost certainly is not. But essentially, you have some columns that are available only to the prover in your system, some columns that are available to both the prover and the verifier, like the fixed column, and some input, some instance, which is available to both the verifier and the prover. And these things are known at various times, but essentially you build in Rust these gates, and these gates eventually get translated into these tables and into these constraints. So this is what a table looks like, obviously with some dummy values. What happens if we look at constraints? Well, abstractly, they can be kind of arbitrary. There's some limitation on how far you can sort of reference things within this table, but essentially, they're polynomials over cells within this table, so you might have something like some ith column in, or some ith row of column A plus, you know, the same row in column B minus that same row in C should be 0, so that, you know, basically we have an addition gate or something like this. Or you can do multiplication, or you can do other things. They can be sort of generic polynomials to some extent, maybe not fully generic. But essentially you have these polynomials over tables. And then what happens is, of course, this is a proof system that's written in Rust, and therefore people have to somehow build this proof system and use it to build applications and do interesting things. And because this is done mostly by humans, and humans are error prone, we have lots of bugs that come up into the real world. Naturally, we've seen this a lot in smart contract security throughout, you know, all of Web3's existence, but also bugs are just not new, and it should be no surprise that zero-knowledge proof systems also have you know, significant classes of bugs, some of which are very difficult and sort of in-depth. Some need a really good understanding of the system to catch, and are probably not something that the average developer will introduce into their code. Rather, it'll be something that's introduced by the people developing that library if it becomes a concern. But others are possibly ones that the end user application can actually introduce into their gates and systems. So in particular, you know, some things here, like I think the frozen heart bug is listed here. I think that's more of an issue with sort of how the proof system was created on the back end, but things like if you don't constrain your cells on that table that we just showed you, that's more the application side. And so, you know, we can't aim to necessarily catch or look for all of them all the time, and it doesn't make sense to do it. But for those application layer ones, certainly we want to see if we can reduce the likelihood of these errors coming into you know, the real world, because obviously people are going to make mistakes. So this collection of bugs is by 0x Park. I think it's a great selection. We're not going to focus on trying to catch all of these bugs. A lot of them are hard. Like I said, some of them don't apply to the application level. But some, like unconstrained cells, or some of the ones near the bottom of that left-hand column, are something that maybe we can look at. And we've been, obviously we're a security company at Quantstamp, so, you know, we've been looking at how bugs manifest in the real world, and how do we catch them, and how do we detect them, and how do we prevent them from happening. And we were looking around at a bunch of zero-knowledge systems, and we found, okay, there's some unique bugs. Obviously, here's a list. You know, what about for Halo2? And while these bugs certainly might apply, we didn't find any tooling to find those. And tooling is very important in any audit that you should get. You should expect some level of tooling to be run, because some things are easier caught by tooling, and some things you know, probably necessitate some tooling if things get really complicated. Some manual inference is probably also going to be necessary, because you can't catch everything automatically. But, you know, we want to see, what could we catch automatically? Is there something we can do beyond just testing? And we started to look, and we didn't see anything for Halo2. We did decide that maybe we can try to do something for Halo2. Because as the next slide will show you, there is some ideas for how to catch some classes of bugs on other proof systems, in particular ones that compile to rank 1 constraint systems. So in this talk, I'll give a very high-level overview of what we're sort of aiming to build and just sort of what we can try to catch automatically. So in particular, we're going to try to focus on sort of 4 classes of bugs. One is under constrained circuits. This is probably the most sort of big problem that we're going to try to capture. It's also the hardest one to try to catch in the code. But we'll also try to see if we can find unused columns or gates. That might be a bug. It might enable an optimization. And assigned but unconstrained cells, because that's also an under-constrained circuit. And we're going to describe this tool sort of as a linter. It's not going to spit out a proof saying you definitely have secure Halo2 circuits at the end of the day. We're not doing that. There's no specification you're going to add to it. There's no sort of heavy formal verification going under the hood. There's just a bit of a SAT solver or SMT solver. And so we envisioned that this is something that if, makes it to production and in the real world, is something that developers can run, and they sort of use it like Slither, and they run it and they say, okay, most of this probably is not going to be something to cause me major concern, but let me just double check the entries to make sure that they're just false positives at worst. And so, as I said, there was some work on automated detection of zero-knowledge bugs in the wild already, but not for Halo2 and not for Rust. So Veradice and others have been working on things like this. I don't remember. I think one of these is Veradice. I think Picus. But also Ecne exists. And both of these aim to do sort of the same thing. They catch some class of bugs on rank 1 constraint system proof systems so that if an app developer goes and writes a circuit in that language, they can check to see that maybe what they intended is actually there in the code, right? That's sort of the end game. And if not, they'll tell you how maybe there's some errors. And so most of them are based on symbolic execution. Often they support custom queries, so we'd like to do the same if we could. And it's automatic in the sense that you sort of just push the button and it spits out some results, and you don't need to worry too much about writing additional stuff if you don't want to. If you do want to, you can. The alternative, Ecne, uses a fixed point algorithm, and you need to specify a little bit. But again, the important part here is that both of these only target rank 1 constraint system inputs, so they don't work out of the box for Halo2. It's conceivable that you could probably massage one format into another, but it seems like a lot of work. So we decided to target the Halo directly and see what we can find. And basically what we're going to try to use is some combination of both these approaches. We're going to use some symbolic execution / SAT solving and some fixed point algorithms, which we'll call abstract interpretation. Okay, so let's use a motivating example to figure out exactly why we're doing this and why this might actually be relevant to you as a developer of these apps, or as someone who wants to build a better tool than this one, because as I said, this is only proof of concept. You can probably do better. Okay, so we'll have a motivating example, and for that, we'll target the first class of bugs we're trying to catch, which is an under-constrained circuit. So we'll say that a Plonkish circuit C is under-constrained is if for a particular assignment of the instance column on the right, which is the input to the circuit, there's 2 satisfying assignments in the advice column that would allow the prover to prove something about this. So this might mean in the real world that you're proving something that you didn't mean to prove, or someone else could prove this, possibly. And that would generally be bad, especially if that extra thing you could prove is an additional transfer of funds in a roll-up or something like this. Right, so this is one definition. There are other definitions that people use for under-constrained circuits out there. We'll use this one. So let's build one of these circuits in Halo2. Okay. If we want to do that, let's take the example and make it very explicit. So here we'll just do the most stupid sort of example we can come up with is just a range check to say, hey, is a number in 0 or 3, right, in our circuit? And we can encode this with a suitable table, which is so small that I'm not going to show it on the screen, with the following constraints. And essentially, we'll have 3 constraints. The first 2 just enforce that the variables representing the bit decomposition of our number are binary. So if it's a number between 0 and 3, you should be able to use 2 bits to represent this number. And both should be binary, and that's what it is here. So for example, B0 times B0 minus 1. B0's got to be 0, 1 to satisfy this. And then the last constraint we'll add is, can you actually decompose your input x to 2 bits, where one of them is just 0 or 1, and the other is going to have 2 or 0, right? And so that's all this example is going to be. And if we want to write this in Halo2, we're going to write something like this. So this is sort of real Halo2 code that is sort of legitimate in the sense, this would be in some app potentially. So we'll write a gate here. We'll say, make sure that B1 is binary, right? And there's a bunch of sort of linguistical stuff there that I don't think I need to dig into, but essentially we encode that polynomial that says, a times a minus 1, a times 1 minus a, and then the system just assumes it's equal to 0, so we don't need to add that explicitly, but it's there. And then I'm a lazy developer, so I'm just going to copy and paste this, make the modifications, and then go to the last gate that matters and say something like, make sure I can decompose my input instance into these types of bits, right? And it's very important to note here, I was a very lazy, very fast developer when I wrote this, right? This might be a problematic circuit. And if we want to try to run that through our system, what we'll do is we'll convert all of that stuff into an instance of a SAT solver. And we'll just say, hey, SAT, can you find 2 satisfying solutions to this? Because if you can do that, we have exactly satisfied the definition of our under-constrained circuit. So what we'll do is we'll hook up a SAT solver into the Rust code directly, and you can do this through various libraries like smtlib or Z3 natively. And essentially you implement some trait or some other relevant component in Rust. And as you build your circuit, you can just sort of query that circuit afterwards and say, give me all the polynomials you got. And then we'll convert them and we'll translate them automatically into something that is acceptable into the SMT library or the solver itself directly. And we'll just say, hey, is it SAT? The answer should be yes. If you have a circuit that's right, you probably have at least one satisfying solution. And then we'll just check to say, can you find me another SAT solution if I tell you at least one variable has to be different in its value in the next model? And if you can do that, then actually we're going to have 2 models for the same problem, and so we're under constraint. I'm going to take a breather here, I'm talking quite fast. And essentially, the tricky part here is this conversion from Halo2 code to the SMT library, but it's sort of not incredibly challenging. I think anyone in this room who's a competent developer could eventually solve that problem. And then we'll see what happens if we actually run it. And very quickly, the code will actually say, yep, we have 2 SAT instances. And I'll show you why on the next case. If you were paying attention on the last slide, you probably already know why. But essentially, the tool within seconds can find that actually we have 2 SAT models. That's not surprising. This is an incredibly trivial example. We don't want this to take hours, right? If it was taking hours, we're probably doing something wrong. But thankfully it passes the sanity check of being fairly quick, and it's very push-buttony, right? So the developer can actually take this, put it through their system and run it, and ideally they get 2 outputs, or it says, nah, you're good. It might also time out. In fact, we expect it to time out on most systems that are sort of real world because they're going to be a lot bigger than this. But it's also nice because if the developer is really interested in improving other properties, in principle too, they can go into the Rust code where you call the solver and add your own constraints. And then you can do things like bounded model checking by adding your own property if you want to see if it holds for a particular SAT instance. Kind of hoping to present that today, but we didn't get a chance to sort of round that out since the last time this talk was given. So push button, but with the optionality of changing things later if you want. And the key part is, yeah, it's all automatic. And so we did find this was under constrained. Why was this under constrained? Well, when I was a lazy, very quick editor or developer, I copied and pasted my gate from the first case into the second one. I only changed the name of the gate, not actually the variable. It's being constrained by that gate. And so what you have is actually there's no constraint on B0 being a binary variable, which is exactly why in the previous slide, in one instance, both of them are binary. In the next instance, B0 is clearly 3, which is not 0 or 1. So this is a contrived example, but it's also possible in the sense that people are lazy. Developers are lazy. We do see this all the time. People make copy and paste errors. Everyone in this room has probably made at least one of these errors in their life. So it does catch something. But as I said, we did also try to find other things we could do because we anticipate that the SAT solving approach won't scale. I can't imagine having the system sort of run on a roll-up and saying, oh, you found all of your satisfying assignments to your instance. I mean, if your polynomials look anything like what the one for the Flonk paper looked like. That's way too many for the SAT software to hold, we anticipate. One of the major outstanding pieces of work for this project is actually figuring out where that limit is, but we do plan to do that, and we're targeting a paper submission by the end of the month, so hopefully we'll have answers for you. For now, let me talk about the other checks we wanted to do. I told you we were talking about 4 different types of checks, and we just went over the example for under constrained circuits, and as you saw, it did work to some extent. We don't know if it'll scale. But another approach that might be sort of obvious and possibly better at scaling is something called abstract interpretation. This is also another classic concept in computer science. It's been around for 40, 50 years. And we started to see if we could figure out ways to get some checks for this, through this method, sorry. And essentially what we can do is we can evaluate the polynomials that we get from our Rust library abstractly, and just sort of say, does it always evaluate to 0? Does it evaluate to something? Or is it definitely not 0? Like it always comes up with some non-zero value. And then when you do that, you can compose these polynomials and these variables that are abstract, and you can see if you can figure out if anything is always 0 all the time, for example, right? And if that's the case, then you get one of these checks, right? You can check that various regions are not constrained, or that some columns are not being used because they're only used in things that always evaluate to 0 and sort of never really important. So there on the bottom there, you can see an example of how evaluating a sum abstractly would work for a polynomial. So basically, if you have sum and multiplication, you get it all. Multiplication is analogous. And so we don't evaluate the polynomials explicitly. We don't have that information. We do it abstractly over some regions. And we can do this because within the Halo2 system, we know which gates are on and off. We can sort of guess, or we can get that information beforehand by sort of setting up the system but not running the system. So we know which gates are on, and we know which polynomials we need to abstractly evaluate. This comes for free from the Rust library through the layouter. And then as a result, as I've already mentioned now, we do get things that check for unused gates. So is there a gate that you wrote down in your file that you never actually referenced? That's probably a bug. People don't write things for nothing. Now, it could just be the selector is off, so maybe you're going to use it another time, but go check it, right? This is why it's a linter, not sort of a prover that you definitely have an error. Do you have unconstrained cells? So is it possible that the values are not what you want them to be? And unused columns. This might be a bug, or it might allow you to optimize your proof system because the number of columns you have affects the runtime of your prover or your verifier, or both, and I can't remember which one it is. But it may also be the case that we don't report anything particularly useful because it will return false negatives at times and say, yeah, I don't know, and in which case you might have some of these issues present, but the technique just couldn't catch it. But we think it's still valuable to have this because there's probably going to be a couple of cases where this does actually happen. So I think I might actually be almost done, talking fairly fast. My apologies. To conclude here quickly, we've got lots of time. I'll give you time for lunch. We're still working on this. If you saw this talk before at Denver, I apologize. It's mostly the same. There was a couple small changes. But essentially, we're trying to build this proof of concept to see what we can catch for Halo2, because we don't think that Halo2 should be omitted from the class of proof systems that can have some level of automated detection. And we're very interested to figure out how that is. Admittedly, we're also spending a lot of time on audits. We're very busy, so we're not prioritizing this project super high. But if you have ideas or suggestions, or if you want to work on this, please let me know, or Mohsen. In particular, we also want to wrap it up and sort of open source it and submit it to a nice academic place to validate the ideas that we're not crazy and missing things that are obvious. That's coming soon. As I've mentioned, we're going to try to do that by the end of the month. And through that process, we'll hopefully solve the rest of the big open questions for this approach, which is, when does it actually stop scaling? Because I sort of expect it won't work for a roll-up, and it obviously works for that very contrived example, but there's somewhere in between where maybe this is very useful and maybe this is not so useful. We also just need to clean up the code base. We don't have things like unit tests or whatever testing would be totally acceptable within the Rust community, and we just want to see if we can catch anything else in this. Ecne and Picus actually catch a much larger class of bugs than we do, so maybe we can take some of those techniques and apply them to our Halo2 checker. I'm not sure how much of that is sort of in the roadmap, but it's definitely something we can consider. So I think that's everything. So if you have questions, feel free to reach out to myself. As I said, my colleague Mohsen is also here on Twitter or Telegram, same handle, or just find me. So thank you. I think there's a mic. Okay. I'm sorry. I'm not having a great time hearing you. Can you say the first question again? I think you got two.
In Halo2, you have lots of arguments, and how you handle that instead?
That's a good question. I don't know. The engineer who would better answer that is unfortunately not here. So I can follow up with you and let you know.
Okay, the second one is that when working in arithmetic instead, you are not handling the finite field, but the set field in the word field. So how you handling the big number field or finite field instead?
Yeah, so I believe that's also one of the parts that's sort of being fixed under the hood to really figure out how that system is being implemented. The idea is to have a finite field solver, and there are works in the literature that do this. I think that's one where we're testing to make sure that we've done that correctly, but it should be something that's kind of custom.
The third question is that in Halo2, you can somehow have rotations and find the current of the next column. So how you actually define a function instead, tracking the cursor of the column. What you need to think about current column, current row, and next row, right? You don't actually know how to handle that.
Okay, so I think the question is how do we look at rotations for like the next row and things like this? Also, unfortunately, a question that I can't answer right now, but I can find the answer from Fatime and we can get back to you on that.
Yes, I'm implementing web assembly too much in code as well. I'm also using stack and you need very slowly implementing this.
Okay, so maybe we can compare notes and then just see what works too, right? It's also possible we're just not doing it yet or can't do it, so like that might be a limit. We'll try. He went to someone else.
Thanks for the talk. Please know which backend resolving you use. Is that free, ZK9?
I believe the current backend is Z3, and we had a suggestion in Denver to switch to CVC5 to see if it performs better. I don't know if that work's been completed. I believe it was being tried last night, literally. So.
I think the core difference you'll find in CVC5 doesn't involve both the memory and both of them.
Okay, so yeah, I mean, I think we want to evaluate both of them before we submit or open source it to see what works, but there also might be issues like the other question asked that are more pressing in the sense of like, are we complete? So.
Well, you also said that you are looking for the case of resolving finite things arithmetic under the hood so that you don't have to do it, right? And one of the things is that CVC5 is supposed to solve that, and sometimes there's actually not.
Yeah, this was exactly the suggestion we had. Sorry, the question was first what solver we're using, and the next one was CVC5 might do a lot of the stuff we want to do for free, and that's sort of why we haven't made substantial feature upgrades in the past couple of weeks, is because we've been trying to swap out the Z3 for the CVC5 to see if we can do something, not just for the sake of evaluating like runtimes, but to see if it's simpler, more elegant. And I don't think that work has been completed just yet.
Thank you. How do you deal with false positives? So the words explain it sounds like a lot
I'm sorry, I didn't catch the question. How do I deal with forced?
false positives.
I'm not sure I understand. I'm still not catching it. I'm sorry. Maybe we can ask this after. Or can you speak a little louder? I'm sorry, I'm not, yeah. Okay.
You know how in the linter, like style of linter, sometimes you want to deviate, so you put some allocation to disable each check when it's no false positive.
Okay, so I think I was hearing some of it. How do we deal with false positives, or how do we deal with annotations to the Halo2 codebase? Is that?
Yeah.
Okay, so the answer is we almost certainly haven't tested the annotations part, and for dealing with false positives, you could presumably just check to see if it's for the under constrained case, you would be able to check by putting those values into it and seeing if it actually passes. It would be nice to have that round trip and done automatically. Right now, you'd have to do that manually if that's entirely feasible, which I don't think we've sort of tested explicitly. So yeah, you'd have to still inspect it.
Right now, Linting is working for Halo2, right? Will you provide support for other Plonkish language?
So it really depends on how much resources we allocate to the project, in the sense that, it started off as sort of not quite a hackathon, somewhere between a hackathon and a real product. So I don't know. If there's demand and we fix all the other issues that may or may not be existing, and it's well received, then sure. And if we open source it, other people can certainly help with that. Right now, I don't know that we're going to spend a bunch of resources on supporting other Plonkish systems. Now, if it's very trivial to do that, if they have sort of the same implementation structure in Rust, where it doesn't take a lot of effort, sure. Will we spend another 2 years on it? Not that we spent 2 years on it now, but will we do that? Probably not. So I don't know, but probably no.
All right, thanks.
Any other questions?